Hi Math 215 students. In this second part of section 1.5, we're going to talk about solution sets to linear systems. Now this is something we've been talking about all semester long, but we're going to say a bit more, and we'll be able to because of things we've talked about since the beginning. All right, for the outcomes for this video, before moving on, please do your best to be able to describe the solution set to a linear system in what's called parametric vector form, and the linear system should be either homogeneous or non-homogeneous. We'll talk about what all of this means in the video. And second, explain the connection between the solution set of ax equals b and the solution set of ax equals 0. All right, so let's dive in. What we want to do is illustrate a solution set using vectors. So we're going to take a look at the system that we introduced in the last video, and you'll remember that we actually found the solution set to this, and we decided that the augmented matrix already was in reduced echelon form. The pivot position is in that first column. It's the only pivot position. So we were able to solve for x1 and add the 4 and subtract the 7, x2 and x3. And then x2 and x3 were both free variables in this very simple system. Then we illustrated a procedure which we'll see a bit more in this video. We kind of took this vector and we noticed that there are a lot of x2s and x3s in there. So if we split the vector into two parts, one vector containing the 4x2 and the x2, in other words, everything that has an x2 attached to it, and the other vector containing the minus 7x3 and the x3, and then the 0 for the second entry. If we were to split it up in this way, we can then factor out the x2 and the x3 as sort of coefficients or parameters for our answer. And so we get x2 times 410 and x3 times negative 701. Now, if you didn't watch the last video, hopefully you're able to sort of follow what's been going on here. But what we want to pay attention to now is that this last expression, x2 times 410 and x3 times negative 701, this is a linear combination of the two vectors shown here. And our solution set is the set of all possible linear combinations, or in other words, our solution set is the span of these two vectors. So in the picture on the right here, I've actually gone ahead and just graphed the equation using a 3D grapher. You'll see that this equation corresponds to a plane. But if we go ahead and sketch the vectors 410 and negative 701, you'll see that these two vectors are them, and they are the vectors that lie in the plane, and together their span is the entire plane. You'll remember that the span of two vectors not pointing in the same direction is actually a plane. All right. So now we need to talk about what parametric vector form is. And the good news is we've already seen it. It's this last kind of expression there. So when you are asked to give your answer or a solution set in parametric vector form, what we're looking for is a collection of vectors with parameters or coefficients attached to them. And to find it for a given system, what we want to do is just what we did. First, you'll want to find the reduced echelon form of the augmented matrix, and that's what we started off here with. Second, you'll want to write each basic variable in terms of any free variables, and remember, the basic variables are the non-free ones. So looking at this matrix, we can tell that there's a pivot position in the x1 column. So x1 will be a basic variable. x2 and x3 belong to columns that don't have any pivot positions, so they're going to be free variables. And so for the second step, what we did is we wrote x1 in terms of x2 and x3. And we just simply solved for x1 in that first equation. We got that x1 was 4x2 minus 7x3. And that's all the second step is really asking you to do, is solve for the non-free variables in terms of the free variables. And then for the third step, you want to write the solutions as x. So that's what we've done here on the right. We're writing our full vector x. But what we want to do is write it with free variable expressions plugged in for the entries that are basic variables. So actually, this is actually the third step as well. We kind of wrote the vector and we substituted our expression for x1 in there. But now comes the magic. We want to split our solution vector up into a linear combination of vectors with the free variables factored out as coefficients. So in other words, we want to split our vector up into a part that has x2 and a part that has x3 because those are our free variables. And once we've separated these two, we can actually factor the x2 and the x3 out in the way that we've shown here. All right, so this is how the fourth step will usually go. You'll usually take a solution that has multiple parts. You'll break it up so that the parts that are similar to each other appear in the same vector, and then you can factor out those free variables at the end. Okay, we will see this a couple times more in the video, but please, if you are asked to give your answer in parametric vector form, please remember how to do that and follow steps similar to these, and you should be fine. All right, so let's go back to picturing our solution sets using vectors. We had just gotten done saying that the graph of this equation is actually a plane in three-dimensional space, but that plane is actually the span of the vectors 4, 1, 0 and negative 7, 0, 1. And in general, the solution set of any homogeneous system is always the span of one or more vectors. Okay, so our system here just had one equation, but it is homogeneous because remember, homogeneous systems have equals 0 at the end of each one of their equations. And it turns out that your answer will always look like this, and so in general, the solution set of a homogeneous system is always the span of one or more vectors. So remember what we said about spans earlier in the chapter. Geometrically, they look like points or lines or planes, or if you were to go into more dimensions than 3, we might call them hyperplanes. And these particular solution sets, these geometric objects, are going to pass through the origin because of the origin being a solution. Remember, the trivial solution was the solution where you set every variable equal to 0, and that corresponds exactly to the origin in your Rn space. Okay, we've talked about solution sets for homogeneous systems. We've given you even a nice geometric description of what the solution sets look like. But what would happen if we were to look at the solution set of a non-homogeneous system? So let's take a look at a very similar system to what we just had. We had earlier the solution x1 minus 4x2 plus 7x3 equals 0. What if we started with x1 minus 4x2 plus 7x3 equals 9? So this system is non-homogeneous because we don't have 0 on the right-hand side of the equation. But if we were to try to solve this, as usual, we would do what we normally do. We would take the augmented matrix and we'd row reduce, except that there's little row reducing to do. We'd end up with a solution x1 equals 9 plus 4x2 minus 7x3. And x2 and x3 would end up being our free variables as before. Now if we go through that separating process, we'll notice that 9 does not have an x2 attached to it, nor an x3. And so what we'll end up doing is taking any numbers that don't have a parameter attached to them, don't have one of those free variables showing up, we'll put them in their own vector, and then we'll separate the x2 vector and the x3 vector as well. Now these vectors that have the free variables are going to be factorable. We'll pull out the x2 and the x3 as before. And so once again, we'll get those same vectors and same coefficients. But now, because of this 9 that was there in the original system, we'll have this extra vector 9, 0, 0. Now, what we said earlier was that this x2 and x3, these were the vectors that gave us the solution set for the homogeneous problem. But now we have something new because we had that 9 there and turned it into a non-homogeneous system. All right, keep this in mind as we take a look at another example. So in this system, we have a system of three equations with three variables. It's definitely non-homogeneous because we don't have zeros anywhere here. But how would we solve this? To find the solution set, well, what we would normally do is start with the augmented matrix. We would row reduce this and solve for any basic variables. Actually, though, if you were paying attention to the last video, these numbers might look a little bit similar. In the last video, we looked at the homogeneous system that had the same left-hand sides of these equations. And we converted this into an augmented matrix form, and then we did row reducing. We've skipped over the details here, but if you were to row reduce and put this in reduced echelon form, this is what it would look like. And then at the end of the story, in that last video, we ended up solving for x1 in terms of x3. x1 is equal to 2.5 times x3. x2 is equal to 0, and x3 was a free variable. So we end up with a solution that looks like x3 times the vector 2.501. And if we let x3 vary as we take the span of this vector, we get all the solutions to the homogeneous problem. Now, we have a non-homogeneous problem, but if the linear system is consistent, so in other words, if there's going to be a solution to the linear system, the steps we do for row reducing are going to be the same as they were before. You can imagine that if we were to row reduce this matrix, one thing we could do is take maybe row 1 and add it to row 3, and we'd end up with a 0, 15, 0, 0. And then we might scale it by 1/15th, and we would get the second equation 0, 1, 1, 0. Now, if I didn't have the zeros at the end there, you can see that we'd probably still do the same thing. It would still be a good idea to add row 2 to row 1 to row 3. And in fact, that's the case. The same row reduction steps for the homogeneous system will also work if you have a non-homogeneous system. So if I were to take the augmented matrix of this system and do the same row reducing steps, I'm going to end up with a reduced echelon form that is pretty much the same in these first columns as the matrix in reduced echelon form for the homogeneous system. Now you'll notice that the homogeneous system had a column of zeros at the end of this matrix, and we have different numbers. When we do the row reducing steps using these numbers, we end up getting -1 and 7 and 0 as the right-hand sides of those equations. But that's fine. We can still solve for x1. x1 is going to be -1 plus 2.5 x3. And x2 will equal 7 now. x3 is still a free variable, so we still write x3 there. And then now we're going to split it up as before. So any part that has an x3 attached to it, I'll put in the second vector there. And any part that doesn't have an x3 attached, I'll put in its own vector there. So we get -1, 7, 0 plus 2.5 x3, 0, and x3. Now factoring out the x3 as before, our answer is in parametric vector form here, which is often what we want. But then if we compare the answer to the previous system, the homogeneous system, that x3 2.501, that was the solution set to the previous system, and it's showing up here in our solution for this non-homogeneous system. So in particular, this behavior happens again. Because we didn't have a homogeneous system, we ended up with a new vector, but that is just added to the solution that we had for the homogeneous system. So is this a thing? Does this always happen? Does it always happen that when you solve a non-homogeneous system, you basically have the solution to the homogeneous system, but with something extra added to it? And it turns out that, yeah, that's what's happening. The solution set of any non-homogeneous system can be formed by adding a vector, something new, to the solution set of the corresponding homogeneous system. Now the vector we add can be actually anything that belongs to the solution set of the non-homogeneous system. So once you have a vector that is a solution, you can find all the vectors by adding your single vector to all of the homogeneous solutions. So, what does this mean for us geometrically? We said before that the solution set to any homogeneous system is going to be a span of some kind. If there are two free variables, more often than not, you'll be dealing with a plane. The span of two vectors is often a plane. If you're dealing with one free variable, the span of a single vector is a line. And so if we imagine what these look like geometrically, what we're doing is taking whatever the solution set of the homogeneous equation, the system was, and we're shifting it by adding a vector to it. So we're kind of moving the plane to a different spot, or moving the line from passing through the origin out to be passing through another point. So let's take a look at this second example. We ended up with -170 and x3 times 2.501 is our solution set for the system this came from. If we kind of take a look at GeoGebra, we've gone ahead and graphed these. We've got the vector 2.501 shown there, and we've got the solution set -170 plus multiples of 2.501, and that solution set is modeled by this line that passes through the plane there. But as we move it around, you can see that that line is parallel to the vector 2.501, and it is shifted away from the origin by that vector -170, as you see there. Okay, so if we were to restate this in slightly more technical language, but with the same meaning, we're going to say that if the equation ax equals b is consistent, and if x is equal to p, if that is a solution, then the solution set of ax equals b is the set of all vectors of the form p plus vh, where vh is any solution to the homogeneous equation ax equals 0. Now, this is a very theoretical theorem. It's not going to help you solve these any differently than before. If you want to solve a non-homogeneous system, you're still going to row reduce, and you're still going to come up with your free variables and write the vector in parametric form and so on. So there's nothing here that will really help you solve these any differently than before, but it is a nice theoretical statement. And in particular, what it allows us to say is something about the geometry. The solution set to any linear system, whether it's homogeneous or non-homogeneous, any linear system, or any vector equation or any matrix vector equation, the solution set is going to form a point or a line or a plane or a hyperplane or whatever, and that shape, that point or line or plane, passes through the origin if and only if the system or equation is homogeneous. If it's not homogeneous, that point or line or plane is going to be shifted away from the origin because of that something new that is added to it. All right, well, before we end the video, there's one final idea that we want to mention. This could be helpful to you, and that is the equation of a line through P parallel to V. So if you're ever asked a question like this, find an equation through the point 1, 2, 3 parallel to 4, 5, 6, and I've written the vectors in single line form here. But what this equation is telling you is that this answer is going to be x equals, and then we'll take the point we're passing through, 1, 2, 3, and we'll add t, a parameter, times v, the vector we're supposed to be parallel to. So since 4, 5, 6 is the vector we're supposed to be parallel to, adding t times 4, 5, 6 finishes our equation for us. Now, if I were to make this a little bit clear, perhaps, what we might want to do is liken this to the equation for a line in 2 dimensions. Now, you probably remember very well the slope-intercept formula, y equals mx plus b. For instance, y equals 2x plus 3 gives us a line through the y-intercept 3, and having slope 2. So we rise 2 for every 1 we travel. Now as you take a look at what these numbers are saying, the b, the y-intercept, kind of functions as a point to start from. We know that our line is going to pass through the point 0, 3. We have a place to start from. Then m is our slope, and that gives us the direction we will be traveling along as we take different values of x. X is going to be all real numbers, and as we look at all the x's possible, we're going to be timesing them each by m, and that gives us the direction that the line travels in. Okay, now for the same reason, when you want to talk about the equation of a line through P parallel to V, we basically have the same situation. Remember that B, our y-intercept, told us where to start. In this equation, P is a vector that tells us where to start. We're going to first step away from the origin in the direction of P, and then we're going to add t plus v, and v is the vector we're supposed to be parallel with. And you can see that as I add a multiple of v, I'm going to be traveling in the same direction as v. And all of the places I can reach by taking p plus tv form a line. And that line will be parallel to v, and it will be passing through p. So the direction that v indicates is kind of like the slope. And just like we had the slope times x, we'll have the slope times t, our parameter that changes. And p, giving our starting point, is very much like the y-intercept being added in the slope-intercept form. All right, with that in mind, we'll review our outcomes one more time. Hopefully now you are able to describe the solution set to any linear system in parametric vector form. And hopefully you remember and can explain the connection between the solution set of ax equals b and the solution set of ax equals 0. If you do have any questions, please feel free to let me know. Otherwise, best wishes, and I'll see you in the next video.